So let me introduce her to you a bit. Prajval Shastri is an astrophysicist over 4 decades, specializing in the physics of supermassive black holes that are found in the centers of galaxies. She investigates the phenomenology of accreting supermassive black holes and their host galaxies with telescopes at multiple frequencies based on Earth as well in space. She got her PhD from TIFR and after postdoctoral positions at University of Texas at Austin and University of California at Berkeley and Harvard Smithsonian Center for Astrophysics. She was a faculty at IIA for 23 years. She has been a Fulbright Fellow at Stanford University and is currently Emeritus Scientist at RRI. She's also adjunct professor at International Center for Radio Astronomy Research, Australia. So later in the afternoon, she will also be giving a talk about her another aspect of her persona, which is basically she thinks a lot about the gender inequity. So she will be talking about that also. And she has a passion for outreach as well. She believes that cultivation of scientific thinking is for everyone, uses astrophysics as a vehicle to engage lay audiences of all ages, etc. So she is also the founder and past chair of Gender and Physics Working Group of IPA. Anyway, we will discuss more on that in the afternoon. But now she's going to give us a talk on accreting supermassive black holes. Let's welcome her.
Yeah. Thank you very much. It's always a pleasure to come here and interact with scientists here. Today, I will talk about accreting supermassive black holes. This is just my long list of collaborators over the years, students in purple who mostly are no longer students and happily continuing to work on accreting supermassive black holes in various places. So the smallest black holes we know are cosmic.
Are you happy with questions?
Yeah. So the smallest black holes we know are cosmic, and heavy stars collapse into black holes at the quote-unquote end of their lives. And we know from dynamical evidence about 70 such, which are scattered all over the Milky Way. And also, of course, more recently, with LIGO and the detection of ripples in the fabric of space-time, we know many, many more, and also extending the mass range of these smallest black holes. But I will not talk about those black holes, but about so-called supermassive black holes, which are those with masses more than 1 million times the mass of our sun. And it will become clear along the way that they are a different beast. So what this image from the movie Interstellar shows is how when stuff comes close to these black holes, they're drawn into it, they swirl around it, accelerate, get accelerated, heated, and shine. And that is the reason we're able to spot them. And so this is a fairly realistic simulation, as all of you know. And so our study mostly hinges on this fact that we're able to spot these supermassive black holes when they so-called accrete matter. So we study them using the whole electromagnetic spectrum, also high energy charged particles, neutrinos, and gravitational waves as well. But mostly what I will show are to do with the electromagnetic spectrum. And these are just some facilities that we use to study these. These are based on the Earth. So you can have visible light and radio facilities, telescopes on the Earth, but because the atmosphere is not transparent at other frequencies, to study the cosmos and also accreting supermassive black holes in X-rays, ultraviolet and infrared, we have to put these telescopes out into space. And the Hubble Space Telescope is primarily a visible light telescope, also observing in infrared and ultraviolet. And it was primarily put in space not because the atmosphere is not transparent, but because the atmosphere distorts images in visible light. And so to get sharp images, the Hubble Space Telescope was launched. And this is just very quickly glimpses of a neutrino facility, and of course LIGO, which you're all very familiar with. And each of these facilities is an engineering feat. So what does it mean to display images at frequencies that we cannot see? Do I need to explain false color images? Or does everybody know what they are? True and false color images? Okay, so this is a real image of a galaxy. If you're an amateur astronomer, you'd be familiar with it. It's called sombrero. And what you're seeing is the distribution of stars. And you're also seeing this dark band, which is not because there are no stars there, but because there's a lot of dust, which obscures the light from the stars behind. And this is what we would call a true color image, because the light detected from the red, green, and blue channels have been mixed in such a way to mimic the human eye. So if the human eye could see sharp images, it would see something like this. All right. Now, images can be represented in multiple ways. We could just have a bunch of numbers, light from each direction, how much light we see as a bunch of numbers. That's very boring. We could have contour images, which was so each contour is the level of a certain intensity that we detect. And during my young days, this is all we had. But that's also kind of boring. Sometimes we still use contours, but the most popular way is what is called false color images. So here is a picture in visible light of a cat. This is an infrared picture actually. So here the colors don't represent real colors, they only represent the intensity. So that is the meaning of a false color image. So the choice of colors is arbitrary. That's why I put this image also. And false color images have meaning only when you give a key, accompanying key to tell you what color is what intensity. You could have a false color image as a sort of mimicking a black and white image also, where you use only one color, but the intensity of the color gives you the intensity of the light detected. So here's that sombrero galaxy again, and the same data is represented here as a false color image in single color. Okay, now the same galaxy was imaged in the X-rays, and you can see, and that is here again false color, and here is the infrared picture. So you can see why we need to image these things at different frequencies, because you can see that the distribution of stars here and stars here is very different, because the stars that are bright in X-rays are a very different beast. And I mentioned this dark band, which represents the dust distribution, and in the infrared it is at that temperature that the dust is seen in emission, and so you can see the dust in this ring-like structure as measured in the infrared range. So this is just a composite of putting all of these things on top of each other. So with computers you can do all of these things. So that's false color images, and most of the things that I show will be real data, false color images, but if it's not real data, I will just say so. So just before I start talking more about supermassive black holes, I just wanted to get a few more basics out of the way. So the fact that the speed of light is finite means, as you know, that we are always out of date as astrophysicists. But that's actually a good thing, because we believe that the universe is homogeneous and isotropic. And so if we want, for example, to learn the history of our own Milky Way, all we have to do is to find another galaxy far away, or many galaxies at different distances, which are purportedly like our Milky Way. And because light has left them a long time ago, we learn about how our Milky Way would have been many millions of years ago, billions of years ago, and so on, right back to the beginnings of the universe. So we measure things in the sky, and so we measure sizes, separation, and so on. Unless we know the distance to whatever we are looking at, we won't know the physical size or the physical separation. So we measure things in angles, and so whether it's separation between two things or the size of an object, they're all measured in angles. And this is just to show you that the moon is about half a degree in size, and this is the Andromeda galaxy, and if we could see it with faintly, it would be much larger than actually the moon, but the human eye can only see the central part. And sharpness of images also are measured in measured and also stated in angles. And so there's a term called angular resolution, which means it is the sort of distance, angular distance between two things that can be just separated by any given telescope. So some of the images that I will show are taken at radio frequencies. So therefore, you know that radio frequency is very low. So by the Rayleigh criterion, the biggest telescopes we can mechanically construct will still have very, very low sharpness or angular resolution. So a technique called interferometry is used, where we decouple so the bigger the telescope dish you have, the more photons you will get, but also the sharper image you will get. Right, but so we decouple that. So we mimic a telescope of, say, this size with two separated telescopes. So we won't get as many photons as this, but if we correlate and these have sensors which are sensitive to the amplitude and phase of the incoming electromagnetic front, and so we correlate them, not add them, correlate them. And then what we get effectively is that we measure with one such pair, like a double slit experiment analog it is, we measure one Fourier component of the Fourier transform of the sky. And so, of course, with one Fourier component, you can't reconstruct the image, so we need many more. So one way to increase that is to have more telescopes. So each of these pairs will give one Fourier component at one instant. And this is the GMRT, which is an example of such an instrument. And we use the Earth's rotation. So if you imagine a bunch of telescopes like this, whose output is correlated, as the Earth rotates, from the perspective of the astrophysical object, the separation that it sees is the projected separation. So that projected separation changes as the Earth rotates. So therefore, if you keep measuring that particular object or that patch of sky while the Earth rotates with a pair, then at each instant, you're measuring a different Fourier component, because the projected size is different. Okay, so that way we increase the number of Fourier components, and therefore we have more components to do the inverse Fourier transform, better images. This is, of course, just very basic stuff. Units of luminosity are usually expressed as the luminosity of the sun. Similarly, mass. Spectroscopy is a very, very important tool in astrophysics, and it's important, of course, to know the composition and the temperature. I'm sure you know this very well, that if you have a source that is a heated, let's say, cloud of gas, if you measure it directly, it will give you an emission line spectrum, which is a composite of all the elements. If it is heated by a background source, you will get an absorption spectrum. This is the continuum spectrum from the source. And one astounding example of this sort of tool used by the application of the Saha equation by Cecilia Payne, there was a discovery that stars were made mostly of hydrogen and helium. Not only that, because of the Doppler effect, if we measure the spectrum of a given, say, cloud of gas in the cosmos, we know the expected frequencies because of laboratory work, and so we can measure the shifts, and so we can determine the speed in the line of sight, either towards us or away from us. So that is again very powerful because it gives us kinematics and therefore dynamics. And of course, there's the expansion of the universe, because of which further objects are cosmologically redshifted more, and therefore the cosmological redshift becomes a measure of the distance of the object. So there's a deeper way of using spectroscopy. So here are just some examples of different spectra. And here is a visible light image of a pair of galaxies that are interacting. And suppose you take a spectrograph, a normal spectrograph that is used on a telescope, it will have a slit. So you put that slit on this galaxy, let's say like that, and you get a spectrum. Then what you're getting is a spectrum of each piece of that galaxy, which was visible in the slit. Now, this is there's a more sophisticated way of doing this, where what we do is you take the image of the galaxy, let's say it falls on, instead of it falling on a sensor, you make it fall on some sort of plate, and imagine you slice that plate physically and tilt those slices, right? So then each piece of the galaxy is on a different slice and it's tilted, so that slice goes to different places in space. So then you can align those strips in one vertical line and pass that through a spectrograph. So now you have a spectrum for each of those strips. Okay, so these strips are like this. You tilt them like this, align them vertically. So each strip, you get a spectrum. But you know exactly what you did. So then you can, in the computer, sort of back calculate. And so effectively, you get a spectrum for each piece of the galaxy. Okay, so in the interferometric technique that I mentioned before, this comes out very naturally because each frequency is again one Fourier component. So in that whole Fourier, inverse Fourier transform, you actually get an image of that patch of sky at different frequencies. Here, it doesn't come out naturally because these are not sensors that are sensitive to the amplitude and phase of the incoming wavefront. So this very sophisticated thing in hardware has to be done. And what we get is called a data cube. So basically, X and Y axes are axes on the sky, and Z is axis of frequency. So at each, in this data cube, I mean, this is just a way of thinking about that data. In this data cube, you can see that you have an image here. So every slice in this data cube gives you an image at that frequency. Whereas a slice taken like this gives you a spectrum of this, a slice of the galaxy. Okay, and this instrument is called integral field unit. It's very boring and doesn't tell you what it is, but here is a representation of what it actually is. Okay, so this is a very, very powerful technique because it tells you the kinematics of everything that you're seeing in each patch of this galaxy, and it tells you what is the spectrum, and the spectrum will be different depending on what is the ionization and what is the temperature and all of that, what are the gas densities. So that takes me to this other diagnostic technique where it's a graphical diagnostic method where we look at the ratios of these different emission lines. So as we know, the in order to excite atoms to higher levels, you need higher frequency photons. So that is the basic idea. And so a given piece of, a given chunk of, say, gas, whether it is excited by light from hot stars, or it is excited by light from this accreting supermassive black hole, or it is excited by shocks. So that can be diagnosed using this graphical method by plotting line ratios. So this is something that was discovered a long time ago, and it continues to be used. So this is the original plot from the paper. On the x-axis is the ratio of the H-alpha line to the nitrogen 2 line. On the y-axis is the ratio of the oxygen 3 to H-beta line. I apologize about oxygen 3, etc. I don't know if you know this, but astrophysicists have this ridiculous habit of calling something with Roman letter 2. Actually, it means it's singly ionized. And Roman number 3 means it's doubly ionized. Okay, so that confusion is there, but you don't have to worry about it. Basically, to get that doubly ionized oxygen excitation, you need higher energy photons. So if you get a lot of that, it means that it must be due to an accreting supermassive black hole. Stars cannot do it. Okay, so that is the kind of idea behind this technique. So we plot these ratios, and this curve kind of delineates objects as between whether it was ionized by an accreting supermassive black hole or stars. So this technique has become pretty sophisticated. Here in these plots, again, you can see these ratios. So sulfur 2 to H-alpha, oxygen 1 to H-alpha, etc. And here it is oxygen 3, which is doubly ionized oxygen. Yeah. Yeah, I'll just come into that. So each point is a galaxy here. So each galaxy was put through the spectroscope. So here we're not looking at pieces of the galaxy, but the whole galaxy as a splotch. Also, yes. Yes, so when you plot these galaxies on this plot, you can see that there's a very distinct pattern. And this curve represents a sort of boundary where all these galaxies have ionization because of stars in them, whereas these galaxies have other things going on, such as accreting supermassive black holes. Okay, so that's just a diagnostic. And one can use, so those were, these plots were where each galaxy is a point, but you can do the same thing for each piece of one galaxy, which is what is done here. This is from some work we did where we were trying to understand what is the impact of the accreting supermassive black hole in the center on the environment in the galaxy. So here is plotted the H-alpha emission from this galaxy in contours. Remember, I said that with that integral field unit, you can get an image at every frequency. So if we take all the frequencies together, which are due to H-alpha, and sum them up and plot, this is what we would see, the contours. And then the colors are the actual ratios. So here it's a ratio of oxygen 3 to H-beta, and this is the ratio of singly ionized nitrogen to H-alpha. So you can see that the images that you get are very different. And so then one can use
in the previous plot,
just be a little louder. I have a little bit of
in the previous plot, a point would be some sort of an integral on this because it's for a galaxy.
So and in the previous plot,
yeah,
it would be as if you did not see anything here, any structure here. You just saw one big splotch.
Okay, so some average.
Yeah, I mean, this galaxy is very close by, so it looks very big. Those galaxies are much further away, so they're just a dot or smudge on the sensor. Okay, so here, for example, again that same ratio. This is again that graphic diagnostic, and so you can see that in blue are the points which fit the idea that they are ionized by stars, and the red are the points which cannot have been ionized by stars and therefore must be ionized by the accreting supermassive black hole, and they are labeled with the distance from the center. So all of these are very close to the center of the galaxy, and these are quite far. You can see 10 arc seconds, etc. So those are these. So the red points are all here, these, and the blue, green, etc. here. So this is just, I mean, no surprise here as such, because indeed you expect accretion from the supermassive black hole to be in the center and therefore have greatest impact in the center and so on. But this is just to give you a sense of the kind of techniques we use. Another tool, nature's tool, is gravitational lensing. And so, as we know, space-time is curved by masses, and therefore light has to bend. And so if you have a very massive entity, such as a galaxy or even a cluster of galaxies, the mass of that, the visible mass plus the dark matter mass, will curve light from objects in the background. And that is what has led to this ring-like structure around it. This is actually just a single galaxy which is in the background of this object. And so then many things can be done. Firstly, we will see galaxies which are much further away more easily, because this is effectively like an amplifier. And then we can do other things as well, such as measure time delays between the different images and so on to infer a whole lot of other physics. I just wanted to mention, does everybody know about the light travel time argument? Or should I? Okay, it's a very, very simple idea that if you imagine an object, a cosmic object, instantaneously becoming more luminous, okay, then what will happen when we are looking at it from here is that we will see the photons from here first, the photons from there last, and then the photons from here in between, right? So we will not see it instantaneously bright. It will take some time. So you can turn that backwards and say that if you saw change in the amount of light from a cosmic object, then that object has to be smaller than the distance covered by light in that time. So that's the light travel time argument. And this is an example of some data where we're measuring the light from an object. It looks very like unimpressive, but you know, the errors are like that much. So you actually, this kind of wavy thing that you see is actually real. It is significant. And so that kind of time scale, for example, a variability here, this is time on the x-axis. So this kind of time scale tells you that if the object has changed on that time scale, it has to be smaller than the distance that light would cover in that time. Okay, so that's the light travel time argument. Another very powerful tool in astrophysics, of course, is computer simulations, which try to represent the best physics we know. And this is just a simulation of two galaxies coming together and interacting gravitationally. And so the point is, it does represent the best physics we know, but it is limited by the computing capacity. And so, you know, the smaller the chunks we can make, the more accurately it will represent the physics, but there's a limitation there. So in fact, what told us that black holes are real was when a supermassive black hole spoke. That's a very interesting story in itself. I'll just give some glimpses of it. So this is an image of a patch of sky, a bunch of nondescript objects. I mean, most of them are stars, like you see the spikes. So stars, some of them may be galaxies, completely nondescript, including this thing. I don't know if you can see the crosshairs, but including this thing in the center here. However, when the spectrum of this thing was taken, instead of seeing a spectrum like this is like a typical stellar spectrum, like even in our sun, you would see the Fraunhofer lines. Instead of seeing a spectrum like that, this object showed an emission line spectrum, which itself was very strange, but on top of which these lines could not be, the patterns could not be recognized as belonging to whatever elements, any combination of elements. So this is just a different way of plotting the same spectrum. So all emission lines. It came to this astrophysicist called Martin Schmidt to realize that if he shifted the whole spectrum by about 16%, then all the lines could be recognized, Balmer lines, etc. And so therefore, if that kind of shift is necessary, and that is cosmological, that means that this object had to be very, very far away. So it's shining like any other star in our Milky Way, right? All the stars have to be in our Milky Way, but it was very far away, which meant that it was enormously luminous, more luminous than the light from all the stars in a galaxy put together. So that was very hard to explain, how a single object could be so luminous. Obviously, that could not be possible by stellar processes. In fact, Martin Schmidt apparently got onto the cover of Time for this discovery. And it was worse than that because it was seen to vary. So I just talked about the light travel time argument. So it was seen to vary on timescales of a few hundred days. And actually, in visible light, it was even much faster than that, which meant that this enormous luminosity, more than 1 billion stars worth, was coming from a very, very compact region, roughly the scale of our solar system. So that was just impossible to explain. Meanwhile, there was the work by Salpeter and Zeldovich and Novikov, who showed that you could harness gravity by this process of matter accreting around a supermassive black hole in order to produce this kind of luminosity. So that was what actually impelled Roger Penrose then to apply much more rigorous the techniques and show that collapse to a singularity of a massive object was inevitable. Until then, it was just seen as a mathematical construct, and so then it all came together, and so the enormous luminosity from a very compact volume of this object called 33273 was explained. There was no looking back after that. So to draw your attention to the spectrum, you can see these emission lines here. Now the lines have a certain width, and you can see that some lines are narrow, like that one, or that one, and that one, sorry, and some lines are broad, like that one and that one. Now the width of these lines, the way we interpret it is that it is due to gas clouds in motion. And so due to motion in the line of sight towards us, away from us, they'll be shifted, but we are not able to see the individual clouds. So we see a blend of all these things. So therefore, the width of the line is taken to be a measure of the velocity dispersion of the clouds that are within our line of sight. So that is how we interpret the width of these lines. And in this case, the width of these broad lines, as we call them, imply a velocity dispersion of more than 1,000 kilometers a second, even up to 50,000 kilometers a second. So therefore, the idea is, although we don't see these individual clouds, so this is not real data, this is just an artist impression. So it's showing the accreting supermassive black hole here. So these clouds, which lead to these very broad lines, must be coming from extremely close to the black hole. And then there are other reasons to think that their geometry is also more in a sort of disk-like rather than swarming around the accreting supermassive black hole. This is an image, that same visible light image, but with a more sensitive instrument, and it's highly saturated, as you can see. And on top of this is overlaid a radio image of the same object, and that is showing you this elongated structure. Now it turns out that if you look at the spectrum of this, it fits in with the idea that it is synchrotron emission. So it's basically telling us that from this entity, there is plasma that is being squirted out in this elongated structure, and we call these things as jets. By the way, why this material has been drawn here, I'll come to in a bit. So there is evidence, yeah.
What we can infer is
the size of the accretion disk, or is it
From what can we infer? The variability, you mean?
Yeah, variability or something.
So yeah, so it depends on, I mean, there are many components to this whole system, right? So so first of all, we'll have to say for a given band, the light that we measure from a given band, we'll have to hypothesize where it is coming from, which component is coming from. And then of course, if it is varying, then yes, it does give us the size of that component. So in the case of the radio emission, turns out it is coming from this jet or the base of the jet. So it tells us the size of that. The visible light is coming from the accretion disk. So the variability tells us about the size of that, and so on. So these are three examples of the very centers of three different galaxies, of which we took these data cubes that I mentioned before. And what is done in these images is the H alpha light is pumped into the green channel, the N2 light into the yellow channel, sorry, H alpha light into the red, N2 into the green, and oxygen 3 or doubly excited oxygen into the blue. And so these are the images that you get when you do that. And so you can see that the oxygen 3 is showing this elongated structure here and here and here, whereas the H alpha N2 combine is more in the form of a ring-like structure here, similarly here. So that is the reason why this thing has been drawn in this sort of torus-like structure, because the hypothesis here is that there's gas in the center of the galaxy around a supermassive black hole. Light from the accretion, the accreting matter, is what photoionizes the gas around, which is the gas in the galaxy. So then why are you not seeing that ionization all around? Why are you seeing it in only these sort of elongated structures? So the idea is that there must be some material around the accreting system which is obscuring this light and preventing it from reaching certain parts of the surrounding galaxy. So this would fit in with these data. So if you had this orangish stuff is meant to represent gas and dust, which is in this torus-like geometry, and so it prevents the light from the accreting system from reaching gas, which is here. It only reaches gas, which is here, which is in the line of sight. So that is the reason why we hypothesize that there is this kind of material in this geometry. We are just barely, with the very, very high-tech telescopes today, barely able to see something like this in a few galaxies. But there is evidence, there is other circumstantial evidence that that is the case, such as this. Also, another piece of evidence, very interesting, in support of this idea is this. So this is an example of a spectrum from the center of this galaxy, where again you see these emission lines, and some of them are narrow like that, and some of them are broad. So here you have two narrow lines sitting on top of a broad line. Here again you have a narrow line sitting on top of a broad line, and these are narrow lines. So the narrow lines means less velocity dispersion, few hundred kilometers per second, and we know that that is coming from, because of imaging, we know that that is coming from these kind of structures here. On the other hand, as I said earlier, the broad lines means high velocity dispersion, and so those must be coming from clouds which are much closer to the accreting black hole. And so then there are objects, meaning galaxies, such as this one, where the central part shows a spectrum with no broad lines at all. Okay, however, you can see here, right, so this is the H beta line, and the H beta line here is very broad, but here it is of the same width as this oxygen 3, this is the oxygen 3 doublet. So they are all of the same width. However, if this is looked at with polarized light, then the broad component pops out. This is this dashed line. the broad component of the H beta. So the way we interpret that is that, so this is again not real data, this is just a representation. So you have the accreting system, you have maybe these jets of plasma, you have this obscuring molecular gas and dust around in a torus-like geometry. So when that torus is face on, you will see the accreting system. When it is edge on like this, you will not see the accreting system, nor will you see those high dispersion clouds, because they're hiding behind this structure, right? However, photons from those clouds come out in this direction, and if there is some scattering material here, then they will get scattered into our line of sight, like a periscope. And so that's why in polarized light, we see the broad component, which is from the clouds which are inside this torus, and we can't see them directly. Okay, so this is again additional evidence as to why we think that there is obscuring gas and dust around the accreting system. So this obscuring gas and dust, for example, will act upon X-rays in different ways. So X-ray emission at hard X-ray energies will come through because this is transparent. Whereas at soft X-ray energies, those photons will be absorbed and they will heat this molecular gas and dust, and the dust will actually shine in the infrared. So this is where we compared the X-ray emission from a bunch of galaxies, some of which were purported to be this kind and some of which were purported to be of this kind. And what we get is consistent in that in the soft X-ray energy band, we see less X-rays from this kind compared to this kind. And in the hard X-ray energy band, the distribution of X-ray emission is more or less similar for the two kinds, and so on. So I think I'll skip that because I might be running out of time. Okay, so this is back to 3C273, that very first supermassive black hole that was discovered. And it turns out that this jet of emission is visible in visible light, in radio light, in X-ray light, and in infrared light. All of those things in false color have been superposed over here. And all these features, you were asking, which component is it the accretion disk or what? So each of these components has its imprint on the overall spectrum that we observe from these objects. So this is the overall total emission that we see from this system, plotted right from radio all the way up to high energy X-rays. And each component will have its imprint and influence the shape of the spectrum. So the spectrum becomes, again, a very important tool for us to study these objects. Okay, so it turns out that every accreting supermassive black hole creates these jets of plasma that are squirted out from the accreting system. So that is why I stuck these two sort of impressions on top of the Gargantua image. So here is one example. This is a visible light image. You can see the sort of spiral structure due to the stars. And this is a false color radio picture of the same thing. Again, in the radio also you see the hints of the spiral structure, but you also see this elongated emission, and this emission is due to these two jets coming out of the central system. Here is another example of the same thing. It turns out that in most of the galaxies, you get these kind of jets which are quenched within the galaxy itself. But in a minority, the jets seem to be launched with extremely high kinetic power, so that they get out of the galaxy itself. So what you're seeing is, this is a false color visible light picture, on top of which is a false color radio picture. So these are all, dots and smudges representing stars and galaxies and so on. Here's a star, but this is the galaxy of our focus, and all of these are the stars in the galaxy. And from the center, this accreting supermassive black hole has squirted out jets which reach outside of the galaxy, hundreds of kiloparsecs, and diffuse out into the intergalactic medium. This is another example of the same thing. Now, with the technique of interferometry that I mentioned before, we can zoom right in to the center and actually see that these are components which are moving. So, did somebody had a question? Yeah.
Regarding the previous slide.
Sorry?
Regarding
regarding
the previous slide. So you said that like this, that the jets which are not quenched would be minority, right? But I was just trying to understand if jets are ejected out like perpendicular to the plane, wouldn't that be the majority? Because like how will you quench if there is nothing to quench it?
No, what I meant is that among all the accreting supermassive black hole systems that we know, most of them produce jets which are quenched. Some of them produce these very high kinetic power jets, and they go well outside the galaxy. And if we measure the speed, because you saw the components moving outwards right here, so if we measure what is the speed, they come out to be faster than the speed of light. And the way to explain that is when if you have relativistic bulk motion of these blobs of plasma which are part of that jet, and they are directed close to the line of sight, then you will get because what we are measuring is the components projected on the plane of the sky. So we can only measure the transverse motion. We can't measure the line of sight speed, because there are no emission lines here, so there's no way to do Doppler shift and measure the line of sight speeds. So we can only measure the transverse speed, and that if the to the line of sight, then in projection, the transverse speed that we measure can come out to be higher than the velocity of light. So in a minority of accreting supermassive black hole systems, these kind of jets are launched. Is that clear? Was that your question?
No, but I mean, I was just trying to understand how, like, what quenches these jets?
So that is a question. That's like the open question. We don't know. So obviously the galactic material in the galaxy will quench. So if you have these jets come out with some kinetic power, but they get mass loaded because there's all this gas, in the galaxy, which will load those jets, then they will get quenched eventually. But some jets don't get quenched. And why is that? Is that because in those galaxies there isn't as much gas? What is the deal? So that's still an open question. First of all, how are these jets made? So the most enduring explanation for these was something proposed in the late 70s and 80s. So the idea is that there's a magnetic field threading this material that is accreting, and then as the accretion proceeds, the magnetic fields twist, and then that creates the pressure to launch the jets. So this mechanism is known as the Blanford-Payne mechanism. It was Blanford and Payne who sort of elaborately suggested it. And so that is the explanation for this kind of jet. But that is still not enough to explain the high kinetic power jets which are launched relativistically. So as far as we know, the other jets are not launched with very high relativistic speeds. Okay, so in this case, so this was an example of faster than light observed speeds and therefore relativistic jets. So here the mechanism is something called the Blanford-Zodiac mechanism, where the spin of the black hole is used. So if you have a black hole that is spinning, then so here this is the representation. So this is not real data, obviously. The representation of the black hole, and this is not the accretion disk now. This is the ergosphere, because you will get, if you have a spinning black hole, then there will be this volume around the black hole where there is frame dragging. So that frame dragging is used in order to launch the jet. So that's the idea here. So you need magnetic fields and you need a spinning black hole. And so these green lines represent magnetic fields which are outside of the ergosphere, and the red lines represent the field lines that cross the ergosphere. So those are frame dragged within the ergosphere, and then that energy creates the pressure to launch these at relativistic speeds. So this is a computer simulation which uses general relativistic magnetohydrodynamics. The green lines represent magnetic fields, the red stuff is material. And so you can see that this simulation actually shows, to our best understanding, that such jets can be launched. And these are at relativistic speeds. So this is how we understand how these jets are launched. But why are they launched only in some galaxies like this and not in others? That is still an open question. Okay, so far whatever I showed you, the only explanation for them was to have a supermassive black hole. But it was still not evidence, direct evidence for a supermassive black hole. And the leap came in with this work, which was started in 1995, basically zooming into the center of our Milky Way and imaging the stars there. So what you're seeing here is a false color picture of the very, very center of the Milky Way in infrared. Each of these splotches is a star. And so these images were taken repeatedly starting 1995. And you can see the date over here. So I'll just play that again. So you can see that since 1995, these stars are shifting, and you can see how they're moving. They're not moving in straight lines, not randomly. They're all moving in elliptical orbits around the same focus, which is why there is that cross there. And not only that, the star of closest approach has approached it and then gone on its elliptical path. So whatever the dark mass that we're seeing here, which is not visible in infrared light, whatever that mass that we're seeing here, which are driving these elliptical orbits, have to be smaller than that distance of closest approach. So the mass turns out to be 4 million solar masses, and it's got to be a black hole. So this work got the Nobel Prize in physics, as you know, in 2020. So this was the first direct evidence for a supermassive black hole, dynamic evidence. And then there was, of course, this, which is a galaxy called Messier 87, shown here in visible light. This is a false color radio light picture. You can see the effects of a jet, which can be imaged, more sharply imaged at multiple frequencies. So radio, visible light, radio, and X-rays. And all of this is inside here. So this is a jet which is going from like that. And then you can see the larger scale structure. The jets have really, gone out and diffused into the intergalactic medium. And you can see that it must have been episodic because the direction is different. See, here it is in this direction, well, now it is in this direction, and even older stuff which has gone on much earlier is in that direction. Now this galaxy already had this is fairly close by, so it had gas clouds which had been observed with the Hubble Space Telescope. You can't see this, but there's a spectrum here, and it shows one cloud with a line peak here, and another cloud with a line peak there. So this is interpreted to be the blue shifted clouds, and this is the red shifted clouds. So there's a separation between the two. So you can get the speed, and therefore you can infer, if the gas clouds are Keplerian, you can infer the mass of the central object that's driving them. And so then there was an estimate of a mass of 6 billion solar masses. And then this object was observed with the so-called Event Horizon Telescope with the same technique, but now at millimeter wave frequencies, which means you're trying to beat the Rayleigh criterion constraint. And so it was the sharpest image ever taken. It's like being able to read a newspaper in Delhi sitting over here. And of course, what we got was the beautiful silhouette of the central supermassive black hole, amounting to zooming in 1 million times into the central part of this galaxy. So the mass of the black hole was confirmed. So now, and then the same thing was done for the center of the Milky Way with the same telescope. And again, a silhouette was seen. So these are two silhouettes we know of black holes, and they were the best case scenarios. It's unlikely we will get more, but again, the very, very direct evidence for supermassive black holes. And spin, as I said, was very, very important in order to explain the launching of the jets. So this is the evidence in favor of that. And what is shown here is an artist impression of what happens when the accreting material around a black hole is prograde with the spin of the black hole. Sorry, this is retrograde, this is prograde, and this is if the black hole were not spinning. So what happens is that the ergosphere that gets created, the radius of that ergosphere is much larger here. So in the retrograde case, the accreting material cannot approach the black hole as closely as if it were in the prograde situation. So now the closer the material approaches, the larger obviously the impact of the black hole and the gravitational redshift that is caused by the massive black hole. So it turns out that this accreting material emits an emission line. It's called the ion K alpha line. It's measurable in X-rays. And so these are sort of representative snapshots of the X-ray spectrum where you see this emission line. So this is the ion K alpha emission line. And so the higher the so it's coming from very close to the black hole. So the black hole has an influence on the profile of the line. And so this tail, which is towards lower energies, is interpreted as due to gravitational redshift. So in the retrograde case, this is all the gravitational redshift you can get, whereas in the prograde case, you can get a much larger redshift. And this is something that has been known for a long time, but the data were very suspect and there were a lot of calibration problems and so on. But when this telescope was launched, this is New Star, it has a very large energy range and so much better spectra than we've ever seen in the X-rays, and so the evidence is pretty clear. So there is, black holes do spin. I mean, there's no doubt anymore about that. I think I should stop, no? There's couple more minutes?
Yeah, you could continue
okay.
for some.
So this is just to summarize what we know, so to answer, sort of try and answer the question that you were raising. So we have one kind which are mildly relativistic jets, which seem to be very often in galaxies which have spiral structure, which means that these are more gaseous, stars are still forming. They have the capacity to expel gas into the intercluster medium. Is it that the black hole is not spinning? No. Meaning, is it that spinning or not spinning of the black hole give rise to low kinetic power jets or high kinetic power? That doesn't seem to be the case, because these black holes also seem to be spinning, and maybe it is Blandford-Payne accretion. The high kinetic power jets, they're highly relativistic. They have evidence for significant magnetic fields. They seem to be in galaxies which are more elliptical, which means that the stars are swarming rather than in a spiral structure with less gas. And they do deposit an energy into the intergalactic medium. Definitely the black holes are spinning, so they are probably Blanford-Snaeg jets. So I'll skip this. So the other complication that we have to contend with when
Prajval, before you go on. So you said the ones that host these really powerful jets could be elliptical galaxies?
Yeah, that mostly that is the case.
How
there
do
are
you
exceptions.
infer that?
Because we can see that they are elliptical and they show jets.
Okay, okay.
It's like very visible.
I see, okay.
Like those images that I showed, no? See this, for example. This is a visible light image, elliptical galaxy, radio image on top of it with the jets. And we have scores of these, like hundreds, thousands, whatever. So the other thing to contend with is this, that it turns out that the mass of the supermassive black hole actually shows a scaling relationship with the mass of the bulge of the galaxy. That means that the stars which are swarming, which therefore is an indicator of the gravitational potential well. And so here is a plot of the mass of that bulge, meaning these stars here, or these stars, and this is the mass of the black hole. Here is the velocity dispersion of those stars, and this is the mass of the black hole. So obviously this kind of a scaling relationship cannot be gravitational, because the scales are just too different, right? So therefore there has to be some other mechanism by which the central black hole and the galaxy grow hand in hand. And so the central black hole can grow in two ways. One is if two black holes coalesce. The other is if the black hole accretes. And it is kind of satisfying that supermassive black holes that are accreting show a similar correlation to the black holes which are not accreting. And so therefore there seems to be a connection between galaxy growth and therefore stellar assembly and the growth of the supermassive black hole. And this is probably mediated by the kind of phenomena that I described before, the accreting material which shines and ionizes and also drives, deposits energy into the gas around. So then the gas would get heated, and that becomes a regulatory mechanism for star formation, because star formation can only occur when gas cools. If you heat the gas, that's going to regulate the star formation mechanism. So this is the idea, and I need to get to the end of the talk. So we do have snapshots of galaxies where clearly they are in the process of merging, and simulations do tell us that if they merge, then their central black holes will also merge to create another, a third galaxy. And yeah, this is an example from my own work where we looked at this galaxy, which is a remnant of such a merger. And indeed, there are two supermassive black holes inside this merger remnant, and we've looked at it with at radio frequencies and at X-ray frequencies, and what we see is evidence for the two accreting supermassive black holes. Also in the radio, the spectrum is synchrotron, so therefore they must be the beginnings of these plasma jets in both cases. And there's also very bright X-ray emission, so that means we are seeing the accreting supermassive black hole. And from the ionization of the gas around, it is very clear from the that diagnostic that I mentioned that these are accreting systems rather than being ionized due to stars and so on. So there are many examples like this, which so therefore when we try and interpret And when we try and look for answers to questions like why do accreting supermassive black holes only create relativistic jets in some galaxies, we have to take all these effects into account. Sorry, I have to skip this because I'm out of time. So I think I will. Okay, maybe mention 2 points. So one point is that more than 50 accreting supermassive black hole systems have been found at redshifts greater than 6. So what this means is that the original idea that we had, that supermassive black holes are the result of the original stars coming together, coalescing, and then gradually building up to 1 million solar masses, is not possible because there's just not enough time for that. So therefore, supermassive black holes must have a different origin, which is what is depicted in this diagram. So it must be that in the very early universe, you had massive clouds of gas which collapsed directly into a black hole of, say, 10,000 solar masses without fragmenting, and without fragmenting in producing stars. So if that happens, then there is headway, and we can get supermassive black holes around 770 million years after the origin of the universe, which is where we need them. This is a gamma ray picture of the sky. This is at low energy gamma rays, and this is at higher energy gamma rays. And this is basically the Milky Way, the band of the Milky Way. And so there are these very large, diffuse, high energy gamma rays which have been seen, which many people interpret as due to activity of the supermassive black hole in the center of our Milky Way, which happened a long time ago. And the James Webb Telescope, about which you have probably heard, can reach out to very, very large distances and has seen galaxies whose light left those galaxies more than 13 gigayears ago. And the James Webb Telescope has actually seen an accreting supermassive black hole very, very early in the universe, 600 million years or less after the origin of the universe. So, therefore, supermassive black holes are a distinct beast compared to stellar mass black holes, not just because they are very massive and they occur mostly in the centers of galaxies, but their origin is likely to be different and not due to stellar collapse. So our questions remain. Our holy grail, of course, is a theory of accreting supermassive black holes. What are the key parameters that can explain all the properties that we see, right? Is it mass, accretion rate, and spin? Or is it age, or what? We still don't have that. We still don't know why some accreting supermassive black holes launch high-powered relativistic jets, and exactly how they impact galaxy assembly and galaxy evolution. So I'll stop there.
Very nice talk. Any questions?
I'll after him. Yeah.
I just want to go back to that question, the previous question I asked. I was just wondering, like, if you want to quench a jet, you would need some material to quench it, right?
Yes.
But I would have expected that in elliptical galaxies you would naturally have that material all around to quench the jet, rather than in spiral galaxies where if it's launched perpendicular to the line of the galaxy, like plane of the galaxy. So I don't understand. But it was the other way around, right?
Yeah. So the spiral galaxies are the galaxies where star formation is currently happening and their gas densities are high. There is cold gas there, all of that. So there's much more gas there. Elliptical galaxies, the current understanding is that they are a consequence of spiral galaxies having merged. And when galaxies merge like that, there is a lot of churning and there is a lot of gas, which is not only driven into the center, but a lot of star formation is induced. So the gas is kind of depleted and it goes into stars. So elliptical galaxies have much less cold gas and all that. I think what you're thinking is a spiral galaxy is sort of flat and these jets can come out and like into intergalactic space. I think that's what you're thinking, right? But the scales are very different. The thickness of the spiral galaxy is quite large, and the accreting system axis is not necessarily, I mean, there's no connection, there's no relationship between the axis of the accreting black hole and the axis of the spiral galaxy. It could be any which way. Okay, so at the scale, you have to think about the scale. The scale at which these jets are being launched, it's like a few thousand Schwarzschild radii, in that kind of scale. So there is plenty of gas. It's not yet reached, like what you're thinking of this spiral galaxy, so there's all empty space here, but the jets are like very inside. So there the densities are. Yeah, Bala.
Yeah, very simple question. Why do you not have these kind of accretion disks around the stellar mass black holes? Is there a
You do. So stellar mass black holes need some stuff, right? I mean, so first of all, protostars have accretion disks. Before the star actually starts, they have accretion disks, the jets are also seen. Once the star has formed, the star forms, then it collapses into a black hole. Where is the stuff? The stuff all goes supernova and is expelled, right? So it needs stuff. So it gets stuff when it is part of a binary system. So if it is gravitationally bound with another star, then that star, when it's in its evolution, it expels stuff. That stuff can get drawn into this. And then it will accrete and it will form what are called X-ray binaries. That's that whole field of research. So X-ray binaries are exactly that. The stuff from the companion star accretes onto this black hole, creates an accretion disk, even jets. So they are called microquasars. There are such objects very much.
So you can expect, for example, some electromagnetic thing coming from these binary black holes of stellar mass origin also, is it?
You mean the Blanford-Nayak jets?
No, any. So, for example,
Yes.
When you look at electromagnetic counterparts now, from the black hole mergers, in the stellar mass case now, people generally keep saying that you may not see them. You will not see from binary black holes, right? Because there's no material around them. So it somehow seems to be very different from the supermassive case. Or am I sort of misinterpreting what is known in?
Yeah, I think, yeah. So you're saying that people are saying that when two stellar mass black holes coalesce, there won't be electromagnetic signatures?
The general feeling is that,
so
it's going to be
yeah, so that is when two supermassive black holes coalesce. See, what I'm saying is one stellar mass black hole and one regular star, which is still undergoing nuclear fusion.
Yeah.
Okay, so that so what will happen is, okay, I think, I mean, I've not thought about this, but I think this is what will happen. So you have a stellar mass black hole. You have its companion, which is a regular star. It's undergoing nuclear fusion. It's burned. Then it expels in the course of its evolution. Some of that stuff comes around this, accretes, and then we see it as an X-ray binary. They're called X-ray binaries. The X-rays are coming from only this, not from that. Then that star, so this will keep on accreting. Eventually, all that stuff will plunge into the black hole. So the stuff will get over. This thing will go along in its life. Eventually, maybe if it has sufficient mass, it might become a black hole. It might become a neutron star. It may not have enough mass. It might become a white dwarf. I don't know. But it might, I mean, yeah, in principle, it could become a black hole. And then those two who would eventually coalesce. But by then, all the stuff is gone, no? So that's why maybe they say, yeah. I'm thinking, I don't know, I'm just thinking on the fly.
Sorry, if I understand Bala's question correctly, it was like if you have a binary black hole merger, you do not expect an electromagnetic counterpart. Now, interpreting your answer, is it like the accretion disk around individual black holes will have some time scale or something? And
yeah, because only as long as there is material.
And by the
Eventually
time they merge, which is like billions of years from forming a binary, you do not expect them to have accretion disk around them, maybe.
Yeah, maybe I'm thinking, because the mass would have been expelled by the star, right? When it collapses at the end, stellar collapse at the end, there's not much stuff left. It's all expelled and it's gone supernova and whatever. So this is also this accreted before, but then the accretion will finish at some point, because all that accretion stuff will plunge into the black hole. So then maybe there's no stuff.
Okay. You showed a very interesting plot of the mass of central supermassive black hole being correlated with the mass of the galaxy, and you made some comment about how it sort of drives the star formation in some way. Can you repeat them?
Yeah, I mean, I that is a whole, it's like a talk for another day kind of thing. I was very cursory about it. So this is an example of a high kinetic power jet. Okay, so what we are seeing here is false color pictures taken in the radio and in X-rays overlaid. Okay, so the pink reddish stuff is the radio picture, and that is showing that there's jets coming out all the way into intergalactic space. If you look carefully at the blue stuff, that is the X-ray image, and this is in a so-called cluster of galaxies, which means a gravitationally bound system of galaxies, and therefore that in that cluster there's a lot of gas, hot gas, just because of the way these clusters evolve. And that gas, hot gas, emits X-rays. So we're able to see that hot gas in X-rays. If you look at this very carefully, you can see that there is an absence of X-rays here. Do you see that? So it's the way it's interpreted is that these jets have gone through this gas and punched cavities in the intercluster medium. So that is an example of how the accreting system is impacting the environment well beyond its gravitational sphere of influence. This gravitational sphere of influence is very small, right? So now the same thing can happen on a galaxy scale also. So you could have, so when those other images that I showed, so for example here, you have this galaxy, right? And it is this square which is imaged here, okay, in radio. And you can see these jets coming out. Now, this jet, it can have two kinds of effect. It could, so there is an accretion disk, obviously. If there's a jet, there must be an accretion disk. So there'll be X-ray light from it that will ionize all the gas and heat it. So then that gas cannot collapse into stars. Okay, so the moment this thing starts, it will start regulating the star formation in the environment. So it will quench star formation. But the opposite can also happen, that if you have these jets coming out like this, they're jets of plasma, so they have momentum, so they'll compress the gas and not necessarily heat it. So then that compression could result in star formation. So it can have both positive and negative effect. So this is This is a sort of plausible way in which star formation can be influenced, but we still don't have a complete explanation that fits with everything that we see. It's still very much work in progress.
So I'm a bit confused about your response to Chandru's question. So are you saying that there is nothing preventing the angular momentum direction of the disk to be perpendicular to the galactic angular momentum direction? Meaning?
Yes. So I'll just show you something that I skipped over. Yeah, maybe this is a good example. So here, this is a whole galaxy, okay? And the scale of this is huge, right? Several tens of kiloparsecs. The accreting system is tiny, 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 right in the middle here, okay? And that is what is shown here. Now, this image is simply a false color image of the same thing, and the green contours is radio emission. So this radio emission is due to all the stars. So you have to think about this massive galaxy with a lot of stars. And yes, it has a spiral structure and therefore it has an axis. Now, but now this thing is in the very, very center. And it's like really zoomed in. So, I've drawn a little square here. You see the square? That is this. Okay, so it's a very small structure. Now here what we are seeing is, this is a radio frequency image. We are seeing a radio jet and we are also seeing this ring of radio emission. And we know that that ring is due to star formation because of the visible light data cube. So this is, you remember I said that H alpha is pumped into red and then N2 into green and oxygen, doubly excited oxygen into blue. So the doubly excited oxygen is like this, you see it? And the H alpha plus N2 is looking gold color, red and, so that is showing like a ring here. So this ring seen in radio is also seen as a star forming ring in visible light. And the oxygen 3 is showing an elongated emission, and that is parallel to the radio jet. And this is synchrotron emission. This is stellar emission, but this is synchrotron emission. Okay, now we interpret this ring as a so-called inner Lindblad resonance. So I don't know if you come across this term, but basically the spiral galaxies in their process of evolution, they're not static, right? These things are moving. They all have the systematic rotational speed, the stars in this galaxy. And in that process, and then there's gas and there's star formation happening, there is this dynamic that builds up and forms structure. So even these spiral arms are not static structures. They are just, density accumulation, which then, which keeps changing. And so then sometimes, like in this galaxy, you can see there is signs of a so-called bar. That is, all the stars get accumulated in a linear structure. And then the spiral arms are at the end and so on. This dynamic keeps happening. In that process, there is a sort of dynamic resonance that happens, which results in stars forming a ring in the very center. Now, because I'm not an expert in that, I'm not sure if the axis of that ring, now this is at a very small scale, that ring is always parallel to the axis of the whole galaxy. I think it is not, because there can be warps and so on in this whole dynamic. So because the scales are so different and so many different things can happen, the axes don't all align, across hundreds of kiloparsecs, because there's so many complicated processes that are happening. What we do find though is that this inner ring does align with the accreting supermassive black hole axis. You can see that here, right? See, this ring is aligning. This ring is now not the accreting system. These are the stars in the vicinity. Is that?
You can have jets which are sometimes kind of off in inclination, and they are not necessarily always perpendicular. Aren't there observations like that of
Jets which are?
Jets which have a bit of sudden break off into.
Oh, yeah. No. There are jets which show, bends and all that. In fact, that very iconic object, the very first supermassive black hole, that actually shows only a jet on one side. Anyway, I can show you later, but this jet, this is a very crummy image. There are nicer images. This jet is only on one side, and very, very sensitive imaging of this thing has been done, and there's no sign of a jet on the other side. So the explanation is that it is hiding behind this jet. So the idea is that if you have something, I mean, if you have anything, like if you take two pens and almost align them but slightly misalign them at close angles to the line of sight, if you project, the angle can be very large, no? So that is the sort of explanation for this. That is one case where there could be a slight misalignment. The other case is where the jets can go out and then misalign. So it could either be because they are part of a binary system, and so there is some precession, or there is something which comes along and gravitationally influences and therefore changes the axis. So yeah, those things are very much known.
Follow. I mean, in one of the latest slides, you showed that regarding the formation of the supermassive black holes, there are these two models where one is when stars, like they accumulate and then they form the supermassive black holes one after the other, or one where you form the supermassive black hole and then stars accumulate and then you form. That's one way of forming a galaxy also, right? You take the supermassive black hole, then form the galaxy, right? But in that case, wouldn't it be the case that these two axes align, because now the supermassive black hole is going to dictate how the galaxy is going to look? So wouldn't in that case you'll have this alignment?
No, I don't think so. Okay, again, that's not my field of work, but you mean this, right? So the idea here is that some gas clouds collapse directly into a black hole without fragmenting and producing stars, but other clouds fragment and produce stars. So they become galaxies, and then these two things merge. So that's the idea. So this black hole seed, it is called, supermassive black hole seed, because the idea is that this is what will lead to supermassive black holes. So this will merge with another galaxy. So then it's not necessarily going to dictate the axis. Does what have to be? Oh, I guess it will eventually sink to the bottom of the gravitational potential well.
Yeah. So the second case that you're talking about, sorry, can you hear me? That's more like in GW sense, the hierarchical merger that people talk about. Is that the scenario, like where you have galaxy merging, and so do the black holes, the supermassive black holes merge, and over a time scale they grow?
Yeah, eventually. But the question is, like, here, the first ones, what were the first ones? Eventually, yes, because I showed examples of merging galaxies, and we see that there's no question that that doesn't happen. and hierarchical merger doesn't happen. The question is, what were the first ones?
Right.
How did the first black hole start? And so this was the original explanation, because in the very early universe, when metallicity was very low, meaning when high, elements beyond lithium were not there, then a gas cloud doesn't cool very efficiently because you don't have all these other atoms. So then you're able to form much more massive stars than in the present day. So it is expected that the protostars, so-called, the very first stars, none of which have been seen so far, were like 200 solar masses or something, roughly. So then you start with a 200 solar mass black hole, and then that kind of coalesces with other 200 solar mass black holes and so on, and gradually builds up to being a supermassive black hole. This was the original idea. But then, if that is the case, you can't have supermassive black holes by 770 million years, which is where we are seeing them. So now that we are seeing them there, we need a different mechanism. So there's a recent paper on another mechanism of dark matter collapsing and so on. I didn't have time to mention it, but that's also quite an interesting idea. I myself haven't fully digested it. It's a recent result.
But there might still be supermassive black holes, like not at the scale that we know right now, but say intermediate mass black holes, say at the center of galaxies, which would just have been formed by the first sort of mechanism of just stars, feeding on stars.
Yeah, but the very annoying thing for us is that we know of stellar mass black holes and we know supermassive black holes, and there's a big gap.
Right.
It's really annoying.
The reason that
no intermediate mass black holes.
Yeah, the reason that I was asking was because there are planned observatories in GW that is aimed at detecting intermediate mass black holes, say, and if that comes about, and if we see that, could that sort of
it could. Yeah. I mean, it would need some directional precision before it can get related to these things. I mean, it'll be good because we'll know that they're there. What kind of object they're associated with, we would need more spatial precision.
Exactly. I mean, if we believe in the first sort of formation channel for these intermediate mass black hole, and say we have a GW signal from some IMBH merger, right? And we're looking at this portion of sky which is big, but there are some known galaxies there. Maybe we could probably correlate it with the galaxy catalogs and probably make a statement.
That could be possible. Yeah, I mean, the search for intermediate mass black holes is a very long-standing one with very little success. I mean, people thought about globular clusters. Globular clusters are those where there are these clouds of gas which formed stars before the whole cloud of gas formed the galaxy. So the Milky Way has many globular clusters around it, as does Andromeda, blah, blah. And there, if you look at the dynamics, people looked for intermediate mass black holes in the center of those, but then the velocity dispersion predicted is very small. So it's a very hard measurement to make. So there's not been much success there. There are these candidates floating around.
Thanks.
But it's still very annoying that there's no definitive evidence. Yeah.
So how one infers the mass of the black hole from quasar observation?
Sorry?
The inference of the mass of the black hole from the quasar observation, how it is done?
How do you measure the mass?
Yeah.
Okay. Very good question. So, okay, so this is a galaxy of stars, okay? And what you're seeing, these dark things again are those dust lanes, we call them. They're regions where there's a lot of dust. And this is the same image. And this green rectangle here represents the spectrograph slit. Okay, so you direct your spectrograph to that direction. So this is the center of this galaxy. I mean, you could put the spectrograph anywhere, but in this case, put here. And this is the spectrum we see. So here, x-axis is frequency, y-axis is on the sky, spatial axis, parallel to this slit. You understand? So now this is the spectrum. So like this is the spectrum from this bit, this is from this bit, etc. Okay. So what you're seeing here is there is roughly, this is the expected center of the line. You can see this is slightly shifted to the blue. Okay, so frequency is, wavelength is increasing in this direction, frequency is increasing in that direction. So this is slightly shifted compared to this, right? So this is telling us that the gas that is here and here are sort of red shifted and blue shifted respectively. But as you approach the center, there's suddenly a huge blue shift. And here suddenly a huge red shift. So that is interpreted as due to the effect of the black hole. So this is where we are crossing effectively the sphere of influence of the black hole. Because until here, it is the overall gravitational potential of due to the, all the stars in the galaxy. And suddenly in this part, you see, it's called a Keplerian rise. You see a sudden increase in the speed. So then using that, you determine the mass. But this is possible only for very, close by galaxies, right? So the Milky Way case was the best case where we can actually image the individual stars and measure their dynamics. But there's no other galaxy for which we can do that, okay, because they're all further away. But we can do this. And this is an emission line, but the same thing could be done with stellar absorption lines. So even if there's no accreting supermassive black hole, the stars, if there is an accreting supermassive black hole, it overwhelms the light from the stars. But if there's no accretion happening, then you can see the absorption spectrum from the stars, and the same thing will be seen. Again, I have maybe after the talk I'll look for that slide and show you. You see a kink in the spectrum, which is that signature, that dynamical signature of a massive object driving the motion. Then, if you go to accreting systems, where's that spectrum? Okay. So with these kind of spectra, okay. Now this spectrum is coming from somewhere here, but we are nowhere near the sharpness that can zoom into the black hole. However, remember I showed that other picture with the that artist's impression. Yeah. So what we think is happening is there is this accreting supermassive black hole, and these green splotches represent the clouds from which these emission lines are coming. Okay. Now, what will happen is these clouds are ionized by the accreting system around the black hole, light from the accreting system. So suppose that accretion changes and the light increases, let us say, then the ionization of these clouds would also increase. And so you will see the line intensity increasing, right? But light would take time to get from the accreting radius up to these clouds. So the brightening in the line will be delayed. It won't happen instantaneously. So by monitoring the light from the accreting system and at the same time monitoring the light from the lines and measuring the time lag, we can measure how far these clouds are from the accreting system. So we can measure their velocity using this dispersion and the radius using this method that I just described. So then Keplerian formula, you can derive the mass. Then it gets more complicated because this is a very, very difficult experiment because you have to keep monitoring these objects for years, hoping for change in the light and then that all of that. And it's technically it's a very, very difficult, just logistically very difficult to do. However, it has been done for a few objects and then using them to calibrate others. Now, just the width, because there's a correlation between the size of this system where these clouds, meaning effectively the radius at which those clouds are, the distance at which those clouds are from the central system, and the luminosity that we see of the accreting system. So then we use a luminosity as a proxy for the size. And then that way determine the mass. So that's how masses of supermassive black holes, outer redshifts, 10 and all that have been measured because we can't, it's using these. So it's kind of a bootstrapping process. You have very accurate, pakka dynamic method, very close, then you sort of bootstrap your way up.
That's a quick question. What is the fraction of galaxies for which we know that there is a supermassive black hole at the center?
Every galaxy virtually that a reasonably sized galaxy seems to have one.
By observations?
Yeah. Wherever we looked, we've obviously not looked at all galaxies.
And for all those galaxies, this mass, black hole mass and galaxy mass relation holds. So the plot that you showed.
Yes,
all those
yeah. I mean, there's a lot of scatter in that plot. So, and that whole process, like I said, that whole process is not understood. Like, for example, there is recently a result where there was, until now, people said it's only the bulge of the galaxy which obeys the scaling relationship and not the mass of the whole galaxy. But then recently there's been some work which shows that in spiral galaxies, even the disk, I think the velocity dispersion, I don't remember now, but the disk also fits with the scaling relationship and all that. So this is all still work in progress. So we don't have an explanation for that huge scatter. Is that because we are not separating different classes of objects or what? So that's all still work in progress. Yeah. Sorry?
What are the differences of jets? What are the differences of jets coming from elliptical and spiral galaxy? Is there any? The differences of jets coming from spiral and elliptical galaxies.
Right. So what we see, where we can see the what kind of host galaxy it is, it's mostly true that elliptical galaxies, the accreting supermassive black holes in elliptical galaxies give rise to these high kinetic power relativistic jets, and accreting supermassive black holes in spiral galaxies give rise to the low kinetic power jets which get quenched within the galaxy. Overall, it's the case, but there are exceptions.
Okay.
Was that your question?
Yeah. I mean, I would have thought the other way around because, initially, that means in the spiral.
You need to speak a little louder.
Okay. So initially, in the spiral galaxy, there is a lot of material available.
Yes.
So the accretion process is active in there. As a result, there should be, jet-driven, longer.
Yeah, so there the thing is, see, in order for accretion to happen, the mass has to come really close to the supermassive black hole. So it has to come really close to the center. That's not easy. As in, there may be gas all over the galaxy. That doesn't, because the black hole is not one vacuum cleaner which goes around, right? It has to approach within its sphere of influence, and that's very hard. It's not so easy to drive gas to the center of the galaxy. And so different mechanisms are invoked. For a long time, people would say bars. You remember I talked about those bars, those formations which come about as a consequence of the dynamics. Those drive, but it never, it's not a very successful idea. Interactions of other galaxies and galaxies merging, that definitely drives gas towards the center of the galaxy. So that is a very plausible explanation. But just because there is gas available around doesn't mean it will come close enough in order to accrete.
Okay, thank you.
Okay, if there are no more questions, and thanks a lot for especially answering all the questions so
Thank you. It
patiently.
was a pleasure.